Okay, this lecture is going to be on special properties of minerals. We're going to look at specific gravity, effervescence, feel, magnetism, taste, tenacity, and fluorescence. To start off with specific gravity, SG is a measurement that determines the density of minerals. Two minerals may be the same size, but their weight may be different. So specific gravity determines how heavy it is by its relative weight to an equal volume of water. So it's kind of a comparison, its weight compared to the same volume of water's weight. So it is definitely related to density. The mineral weight over weight of equal water volume, and that's the key difference here. Specific gravity is its heft, and that's kind of a term that says how heavy it feels. Where let's compare pyrite to feldspar. Pyrite has a heft to it. It's a high density. So compared to, say, a feldspar, it would have more heft essentially, and therefore pyrite just feels heavier. So if I'm comparing this to this, these are both my feldspars. The next one we'll look at is effervescence. This is where a chemical reaction takes place with a weak acid, and the weak acid will be HCl. When we drop HCl onto a carbonate mineral, a CO3 group, as you can see, calcite is calcium carbonate, and here's our HCl, and we observe bubbling. This is called, in the case of with calcite, a vigorous effervescence. We confirm that the mineral contains a carbonate, in this case calcite. Rocks such as limestone are composed almost purely calcite, and these will effervesce vigorously. So we'll use it as an indicator for not only the presence of a carbonate, but for calcite when it effervesces vigorously. This is the key here. I want you to look at the reaction, the products that are produced, carbon dioxide and water, and we get our calcium and chlorine, and these all balance. This is a balanced reaction, but I want you to pay attention. This is what's happening in the effervescence of dropping the weak acid onto the calcite itself, the mineral. When HCl is dropped onto a mineral and we see a mild effervescence, we're going to confirm that the mineral is dolomite. We're not going to be looking at a lot of different carbonates. We're only going to be looking at calcite and dolomite. And dolomite is similar to calcite in that it is a carbonate group. It contains CO3, but the slow manner in which it effervesces tells us that it's different than calcite. It actually has magnesium within its structure, molecular structure. And the feel of a mineral. So this is a real simple one. The feel of a mineral can be a simple way to begin identifying a mineral, but just like with color, you would want to do more testing. The two minerals here I have graphite and here's talc, and they definitely have very distinctive greasy feels to them. Moving forward with magnetism, we can find that magnetism is a unique property of lodestone, one of the earliest compasses of mankind. Lodestone is of the magnetic variety magnetite, which are only found in a few deposits throughout the world. Although it's only weakly magnetic, its magnetism is definitely discernible. So you could even find magnets and iron filings will stick to the magnetite. And essentially here's what we have going on. A simple bar magnet kind of illustrates what's happening within the atoms of the magnetite itself. It's going to have a north and a south pole, and it's going to have a magnetic field around it. And you can see these iron filings here kind of orienting themselves based on the field that's generated from the magnetism taking place here. So what's happening? Well, magnetite has an alignment in its iron atoms, and you can see down here, if we compare these two pictures, that if we had a nail that was not magnetic, you're going to find that the north and the south poles, let's just call these all the iron within the nail itself. And all of these are going to be oriented in different directions. So magnetism, even weak magnetism, is the result of the atomic domains in iron, nickel and cobalt minerals, and their combined motions of the electrons that they are composed of. So notice we can actually orient these iron atoms, and if they're all oriented a certain way, you would find that we would actually create, this would actually have we'd have the north and south poles. If this is the iron atoms, the electrons are going to be spinning perpendicular to this. It's going to be generating the magnetic field here. In this case, we have an electromagnetic situation to where we're going to be generating a weak magnetic field, and hence it's going to have some weak properties of magnetism. So it has everything to do with the atomic domains and their combined motions of their electrons. So the taste of a mineral, and I'm definitely not encouraging you to taste them. It's never a good idea to taste a mineral, but halite or table salt would taste salty, right? Don't overthink this. So where did the massive salt mines come from, right? We've got salt accessible in the United States or all over Europe. different parts of Asia. Actually, some past civilizations based their entire currency around them, and Roman soldiers were paid in salt. So salt has been a pretty significant mineral over the years, over history. Oceans dried up and the salt precipitated. It was left behind. As continents moved due to plate tectonics, land was pushed upwards. So ocean water would have been left behind in pockets or even in small lakes or even large lakes. As it evaporated, as the water from the oceans that were then becoming lakes, salt was produced in mass quantities. Here's a picture of a no-no. Don't go out and just start licking rocks. It's not a good idea. Here's a picture of halite. It's cubic crystal form. Here's just an example of a lake that has just dried up over time, even in modern human history. That it happens when there's a net loss of evaporation, as opposed to the replenishing of runoff. It's gonna change. It's gonna change very dramatically. And here we find a bunch of salt build up here, and I don't even know where this picture was taken from. I like the picture of salt here, and we have ocean water, seawater out here, and every time that waves come in and crash, and it goes back over time, it's gonna precipitate into the salt itself. But I want to look at the United States map here. That salt here, it's safe to say that the United States was covered with ocean water at one point. Now, it's got a deep history, so we've got 4.6 billion years to work from. So the salt we find in different locations is because ocean water had dried up and left it behind. So moving on into minerals tenacity. Tenacity is the resistance that a mineral offers to breaking, crushing, bending, cutting, or other acts of destruction. Where fracture is how a mineral breaks once the tenacious limit has been exceeded. Tenacity describes the mineral's response to stress. So you've probably heard the word, oh, this sports team has a lot of tenacity, or they have tenacious D, but they essentially respond well to stress. We can talk a couple different types of tenacity. We can say brittle. It breaks easily or is crushed into a powder, for example, kaolinite. It can be sectile, can be separated or cut with a knife, for example, gypsum. It can be malleable, can be flattened by hammer, gold and silver. We could even put copper in that. We can talk about ductile, can be stretched into a wire, right? All true metals, particularly copper. Flexible but inelastic, it bends and it stays in its new position, right? Copper and gold, they are very highly, it's also another kind of a way of describing malleable. But flexible but elastic, it bends but it springs back to its original position, and your micas exhibit that. We can bend it. It's actually very weak vertically with bonds, but it's actually relatively strong pulling it apart. And lastly, fluorescent minerals. Fluorescent minerals look really cool. This unique property has everything to do with the atoms of the mineral. Fluorescence generally needs an activator impurity, so all of these have something that's going to be, let's just say, fluorescing. Some minerals can fluoresce in many colors, depending on the wavelength of the UV light shined upon them. Calcite can be red, blue, white, pink, green, and orange. So a lot of these actually contain calcite. So why does a mineral glow in ultraviolet light? Well, all minerals have the ability to reflect light. That is what makes them visible to the human eye. But some minerals fluoresce in the presence of UV light. Incoming UV light is absorbed by the atoms within the mineral we're looking at. But this bumps valence electrons to a higher energy state temporarily. And as the electrons fall back to their ground state, which is stable, a photon is emitted at a different wavelength, in the color, which leads to the colorful light that we see. So let's look at this picture here. So how fluorescence works. We have incoming light, we have ultraviolet light here. A photon strikes the electron within the mineral. The impact energy excites the electron and it temporarily jumps up to a higher energy state. Notice it goes from one state to a higher state. The excited electron falls back to its ground state, and in the process it emits, in this case, the electron loses some of its stored energy and emits a photon at a longer wavelength. So in summary, fluorescing minerals. Minerals glow by applying the concept of valence electrons jumping to a higher energy state by ultraviolet light, right? UV light is just energy. UV light, a pure form of energy, excites valence electrons to a higher energy level. It's a quantum state change. And the electron falls back to a stable state or ground state. It emits light. So we have this collision, boom, kicks it to a higher state. As it falls back, it's going to emit. So here's our incoming sunlight, or excuse me, ultraviolet light. Kicks it to a higher energy state, and when it falls back, it emits a photon of light of a longer wavelength. And here's a video I created for just the 6 properties that we'll be focusing on in class: effervescence, magnetism, tenacity, taste, feel, and fluorescence.